thank you very much to Professor Atsuhiro Nakamoto for a very nice talk on the flip distance of triangulation on surfaces. Okay, before we go to the third speaker, I'd like to tell the participants who want to ask questions. So for those who join us on the Zoom meeting, you can start to write your question via the chat room. Please tell your name and your affiliation and your question. And then I will help to read the question on the question and answer session. So now we are welcoming our third speaker from Yokohama, Associate Professor Kenta Ozeki, who will talk about a list orientation of a graph. Professor Kenta, can you hear us?
Yes, I can hear you.
Yeah. Good afternoon, Professor Kenta. So you may share your screen.
Sure. First, Professor Nakamoto, could you close yours?
I don't know. Okay. Okay.
Yes, can you see the slide?
Yes, we can see it clearly.
Okay, good. Can I begin?
Yeah, you can start, Professor Kenta.
Okay, thank you. Thank you for the introduction, and thank you so much for organizing that nice workshop. And I'm so happy to give a talk in this workshop. Yeah, fortunately, I also join in online and hope I can visit your place in future. But yeah, I'd like to give a talk about my recent research on list orientation of a graph. Sorry, this should be removed. And this is a joint work of some people from Iran. And also, I worked with my former student, Toshiki Abe. Yeah, before proceeding the main part of my talk, I'd like to give you one puzzle related to our result. So this is a table for round robin tournament. So you may think that some game like football or volleyball and so on. So now there are 6 teams, and each pair of 2 teams have exactly one match, one game, and no draw. One team wins and one team loses, right? But I am not interested in which team is the strongest, but I'd like to see some result. Okay, before going to the matches, we first ask each team how many wins do they want. So one team may say that they want to win all games. Yeah, that's possible. Or some team may say that they want to win at least half games. So in this case, at least 3 games they want to win. And like that, each team says something which is the number of wins they want to have. So I'm interested in that under these constraints, whether there is a result of the tournament which meets all of the requirements. So in this case, we have a result like this, which meets all of the requirements. So like team A wins all games as required. Team B wins 3 games, which is as required by team B, and so on. So like this, I'm interested in whether there is a result meeting all of the requirements. So, so sorry with that. Okay, so, but we also think the little bit strange situations where each team may say that the strength, some numbers, which is the number of wins they want, but sometimes they may be strange. Okay, team A may say that they want to win 3, 4, 5 games. That might be possible. But some team may say that non-consecutive numbers. In this case, team B says that they want to win in 2, 3, or 5 games. They do not want to win exactly 4 games. Like that, each team says some numbers which may not be consecutive. But under this situation, I'm interested in whether there is a result which meets all of the requirements. Like that. So in this case, there is. Actually, this result meets all of the requirements. Team A wants 5 games. Team B wants 3 games, and so on. This seems so strange because each team may want to win as many games as possible. So no team says that they want to win in 0, 1, or 4 games. I don't know why they do not want to win in 3 or 2 games or 5 games. But this is a mathematical puzzle. So even in such natural situations, we'd like to find whether there is a result of tournament which meets all of the requirements. So this is the task. And okay, so this is related to the main target. So I now check this sum. So I should note that the sum of the wands is exactly the number of matches, of course. And in this case, the sum is equal to 6 to choose 2, so which is 15, I guess. Like that. Okay, so I give a statement, precise statement of this case. So find the smallest integer fn satisfying these conditions. So we have a round robin tournament by n teams. And each team says fn numbers in the numbers between 0 to n minus 1 as a possible number of wins. And our task is to find the result meeting all teams' requirements. Of course, each team says many numbers. It is more likely we can find the result meeting all of the requirements. So the problem is that how many teams they need to say, okay, each team needs to say to find result meeting all requirements always. This is a problem, and in our researches, we show that this number is between half of n and 2,000 n. But we could not find exact value for these questions. But we conjecture that the lower bound should be equal. I don't know. Also, I will explain that later, but even in the case where n equals 6, we have no result. We do not have an exact value. So even in this situation, we now know that if each team says only 3 numbers, there are some bad choices, which means that there are some numbers of each team where we have no result meeting all of the requirements. But we don't know whether number 4 is enough, which means that we don't know whether if each team says 4 numbers, whether we can always find a result meeting all requirements. That's an open problem. So this comes from just a puzzle, but we would like to think this puzzle in a graph theory point of view. So then we call it L orientation. I'd like to define that meaning. So we are interested in the graph, so we consider the graph theory problem. And orientation of a graph means that the operation to obtain a direction to each edges. So we are given an undirected graph like this, and then we give a direction to each edge. This operation is called orientation. So in the world of a round trip tournament, it means that each vertex corresponds to each team, and each edge corresponds to one game. As I wrote on the right top, if one team wants the game against the opponent, then we put the directions from a team who wants to a team who lost. So that orientation means that to get the result of the games. And the number of wins of each team correspond to the out degree of each vertex. So the out degree means that the number of edges outgoing from that vertex. So for example, in this vertex, there are 2 edges leaving from that vertex, so the out degree is equal to 2. But this vertex has only 1 edges outgoing from that vertex, so the out degree is equal to 1. Like that, the out degree corresponds to the number of wins of that team. And we consider the problem in the puzzle I already introduced. So for each vertex, there is a set of numbers which correspond to the numbers which they want to win. So each vertex have a list of the numbers. For example, this vertex has a number J1, this vertex has number J2, like so on. With the list given, we consider an L orientation of the graph, which is an orientation such that the out degree is in the list. So in this example, from a given graph with a given list, we have this orientation. So you see that this vertex has out degree 2, which is in the list. This vertex has out degree 1, which is in the list. So all vertices have an out degree which is contained in the list. So this orientation is said to be an L orientation of the graph. So to obtain, in the puzzle I explained, to obtain a result meeting all of the requirements means an L orientation of a corresponding graph. So in the terminology of graph theory, we want to consider an L orientation of a given graph together with a given list. Okay, I begin with some puzzle, but this problem is related to some important classical topics in graph theories. In the graph theory terminology, the orientation corresponds to correspond to a linkage problem. So if you want to move some items in the network to some branches, that such a problem, some of the such problem can be translated into some orientation problem. So there are many works on orientation in graph theory, and using such a result, we have we can solve an L orientation problem for some special cases. For example, if the list, all of the list is just an interval like this, from 1 to 3, from 0 to 1, and so on. If all lists are intervals, this problem can be solved in polynomial time. So we have a good algorithm to decide whether there is an L orientation from a given graph and given list. But in the general case, it is known that the problem is NP complete, so it must be hard, tough problem. And interestingly, if the list have some modular conditions like 0, 3, 6, 9, or 1, 5, 9, like that, if it satisfies the modular conditions, then the problem, L orientation problem, is related to K-flow conjecture. It's a big conjecture in graph theory. So like that, this problem is related to the important area of graph theory. But so we consider this problem, L orientation problem, looking at such a relation to such important topics in graph theory. And also we'd like to think how to find an L orientation in a given graph. And especially in my talk, I will focus on K-regular graphs. So each vertex has the same degree K. And if the list is huge enough compared with K, then we'd like to find an L orientation. We consider this problem, but to do that, I give us some exercise related to that. So there are 3 examples, 3 graphs with some lists. So those does not have an L orientations. But the problem is that why they do not have the L orientation. And those reasons will give us some future for this problem. So I'd like to explain the reason why they do not have L orientation. So the first problem, you may think by yourself like that. So the first problem is with this graph, with the list 0, 1 for all brushes. And the second one is just a C5 with the list 0, 2 for all brushes. The third one is a complete graph of order 5 with this list. If you are interested in, then please think by yourself that one, but I'd like to explain this. So the first one is a little bit easy. So this all brushes has a list 0, 1. So in some sense, if you want to find an L orientation, the number, the outer degree can be only the small numbers, only at most 1. That's a problem. If you try, you can soon find that the edge cannot have a direction because of the out degree constraints. So in this case, to satisfy the out degree at most 1, you can give a direction to only 6 edges. But there are 9 edges. There are too many edges compared with out degree conditions. So too many edges compared with out degrees, which is required from the list. That's a problem for the first case. And more generally, we see that some problem happens for general k-regular graphs. So let it be a k-regular graph where k is odd, and we put this list to all bushes. Then there is no L orientations. So the problem is that now in the undirected graph G, each vertex has degree k, so there are k edges to incident to each vertex. But from the list, in the L orientation, if it exists, it can have strictly less than half of k edges outgoing from that vertex. So there are too many edges. So more precisely, I can explain like that. So if there is an L orientation, then we can calculate like this. So first, first we have this equality. So the number of edges is the sum of our degree. Both each edge has a one direction. So the number of edges in the graph is the sum of the our degrees. But each out degree is at most this number. So the sum is bounded with this. But using the handshaking lemmas, both it is smaller than the number of edges. So we have a contradiction. The number of edges is less than number of edges. That's a contradiction. So we conclude that this graph G has no L orientation. So in this case, the size of the list is this value, k plus 1, half of k plus 1. Even with this huge number of lists, there is a bad example, some example which doesn't have an L orientation. So that's the issue. So we may obtain some result, assuming a larger list give us an L orientation always. And we prove that this is the case for bipartite graph. So for bipartite k-regular graph, if you give a list of this huge size, we can always find an L orientation. This is only for bipartite graph, but we have a positive result. So I do not explain, sorry, I have no time to explain the detail of this proof, but this is only for bipartite graph, unfortunately, and for non-bipartite graphs, that size is not enough, which I will explain next. So to explain the reason why the size is not enough, we should think the two exercises. So the second exercise is the case C5 with the list 02. Maybe it's the reason is very easy. So because of the restriction of the out degree, the direction of the edge must alternate along the cycles. To keep the degree 2, if we put this direction, then the next, the edge must have the direction like this, but then, and so on. So you have a alternative directions on along the edges, but this is an odd cycle, so there are no way to complete. This concludes there is no error orientation of this graph. Okay, this is a reason, but I give another reason for another explanation why this doesn't have an error orientation using this inequality which appeared before. So the number of total edges is equal to the degree sum. But in this example, the number of edges is 5. This is odd numbers, of course. But if there is an error orientation with this list, all our degrees must be even, 0 or 2 must be even. So in this equality, the left is odd, while the right must be even, which is a contradiction. So because of the parity constraint, there is no error orientation with this example. And this parity conditions can be generalized for other cases. So suppose a k-regular graph with k even, but the number of edges is odd. Take such a graph and put this list to all bushes, taking all possible even numbers. We put this list to all bushes, and then by the same reason as above, there is no error orientation of the graph by the parity problem. And the list has a side, this is the one. And this value is slightly larger than the previous one. So even if we put such a huge set of numbers to each vertex, there still no error orientation of the graph. I should notice that such graph, there is no bipartite graph satisfying these conditions. So this doesn't conflict our previous theorem, but if we think a non-bipartite graph, we need to think these parity conditions. And there are another example which is more strange, but actually there is. The third example, which doesn't have an error orientation, I explain the reason. So suppose there is an error orientation of this graph, and suppose this vertex has out degree 4. So in this case, this vertex has degree 4 and out degree 4, which means that all edges incident to this vertex must be outgoing from that vertex. So we can observe that other vertices cannot have out degree 4 because one edge is incoming already. So this vertex cannot have out degree 4. And of course, all others cannot have out degree 4. So each vertex, each other vertices, all of the other vertices can have out degree 0 or 1. But then there are too many edges remains to have the out degree 0 or 1. So that's the problem. So the list seems strange, but in this situation, if you take a huge out degree for some vertices, we have too many edges remain. That's an issue. We can generalize this result like that. So if we take a complete graph of order k plus 1, where k is even, and if you take this list to all vertices, there is no error orientation So the point is that we have a value k together with small numbers. So the list seems strange, but this list has size that number, which is the same as the previous example, but there is no L orientations. And yeah, I only explained the case of a complete graph, but there are more examples. So anyway, we have some example with this size, but does not have a L orientation. So we assume a little bit more, and this is our main conjectures. So any graph, any k-regular graph, if you put a list of this huge size, that graph always have a L orientation. That's our conjecture. And studied many cases, but we couldn't solve this. This conjecture is open even for complete graphs. So I think this is natural conjectures questions, but it's still open. Maybe I need to. So we have some result about that. So there are some special cases for that. So we solve some special cases that yeah, unfortunately this is open question, open problems. And even in the case of complete graph, this is unsolved. So what we obtain for complete graph is a case where each vertex has this huge list. So and assuming this, and assuming each vertex have such a huge number of lists, then we always find an L orientation. Or even for these conjectures, if all lists are the same, then we show that there is an L orientation. But generally, that conjecture remains. So I explain some possible open problems which can be tried. In some sense, I introduce some reasonable problems which may be able to obtain the answers. So actually, the next open case is case 6 with the list size 4. But even in that case, I have no answer to that. The list size 4, I don't know whether the list size 4 is enough or not. So this is still open. I have no idea how to attack that. As I explained, if the list is same for all buses, we could prove there is always an L orientation. But for the next case, we don't know what happens if there are two types of list. We may think following the proof of this result, but it might be difficult. I don't know. Or you may consider the problem fixing the list. But from some technical reason, this list seems tough. The list having the small numbers and also big numbers, or something similar to this. That list seems tough concerning some to prove the general cases. So it was trying to the case with this list or similar lists with this. So focusing the fixing some particular lists, it is worth trying to as a step to attack the general cases. So I propose those questions to obtain the general result. So that might be interesting and important step for the conjectures. Yeah, I think I prepared some results, but I think it's almost a time to end. Maybe I break the time restriction. Sorry about that. So I like to stop my talk with those open problems, and hope you are interested in and try to them. And thank you for listening.
Okay, thank you so much for Professor Kenta for the interesting talk. So I think there are more slides. So for those who are interested in reading more slides, maybe you can contact Professor Kenta to get the slide probably. Okay, before we go to the question and answer session, let us first thank the three speakers, Professor Sayar, Professor Atsuhiro, and Professor Kenta by giving an applause. Okay, so now we are going to do the question and answer session. For those who join us online, you may write your question on the chat room, or you can ask directly to the three speakers, or maybe there are any question from the participants who are here on site. Please. Yes, please. Please introduce your name and the university.
Thank you. Good afternoon. Thank you for the chance. I'm from Ganesha University. My question is, sorry if I mistake to call the theory, the name of the theory. I forgot the name. My question is for the speaker one. I have something interesting with the topic of the Ramsey theorem for the universe. I'm a physicist. I study about gravitation, and that's if I study about Einstein gravitation, there is the application in cosmology. Cosmology is one modeling of the universe. Okay, when we discuss about Einstein gravity, we use the Riemann geometry with the Levi-Civita connection, and if we describe the dynamic of the universe by the Einstein field equation, and we have to solve this equation, and the solving of this equation, we get the model of the universe. Okay, my question is, maybe that's related about that theory, and if it's related, what is the correlation need, and what the compare it with R in there, the function R in there. I think that's something in there. I think that that's my question. Thank you, and thank you for the chance.
Okay, I should answer her. So, but a difficult question. And she are studying about Riemann geometry. But in the universe, there are many systems of the planets. And it should be making some stereographical structures. For example, and recently I read some book. The title is the book before we should read. I said, so sorry. The title is just Japanese. Just a book that should be read. I read this before we meet alien. So we have our solar system has only one sun, but this is a very rare case. So usually sun system, right, consists of many suns together. And the surrounding the planets, many planets going around. Such system has some spherical relationship. Can you understand by the using Riemann geometry? So I said in my talk, I never calculate anything and also not try to solve differential equations. So in the space, in the universe, in the world, there are many things, combinatorial structures cannot analyze in such a differential methods. So I'm just talking about my dreams, so not so mathematical. So, but I think answer to your question, I think enough. Thank you.
Okay, thank you, Professor Saya, for the answer. Is there any other question from the participants? Or maybe I have one. So I have two actually. So my first question is for Professor Saya for the first talk. So you talk about Ramsey theorem for complete graphs, but as we know that in the real world, not all huge network can be represented using complete graphs because there might be many edges missing. Are you aware of any research or any result about graphs that come from a huge network, from the real networks? And is there any study on some version, maybe different version of Ramsey theorem on this type of graphs?
Sorry, I never I slowed the question to the Kenta. Kenta knows many things about the Ramsey theorem. I'm basically the geometers, not combinatorians people. So I don't know the details of the Ramsey theorem. Please answer, Kenta. Sorry.
Neither to me, I'm not the expert of the Ramsey theory, but there are many researches for not only complete graph, but also many types of graphs. So, I think that nobody considers the relation to the real network. Just in mathematics, they study to find the Ramsey number for many graphs. So if you check some, for example, some survey papers, you may find something interesting to you. I'm sorry, I don't know so much, but I just can say that there is a good survey on that.
Okay, thank you so much for the answer, Professor Kenta. I again welcome the participants if you have any question. Okay, if there is no question, let me ask one more, because we have more than 100 participants online and there are some participants who are still here. It's 5:35 in Balinese time now, but they are still very enthusiastic to attend this workshop. So probably from these 100 participants, I think there are many lecturers from mathematics or natural sciences, or maybe from computer sciences, or maybe there are some undergraduate students. And among the lecturers, I think most of us teach in undergraduate programs. So I know that Ramsey type theorem or Wagner theorem are really famous, and it has been widely studied over the years by the graph theorists. And I think the problems of round robin problems or list orientation of graphs is also interesting. But can you give some idea to us whether these topics are difficult? I mean, how complex are these topics? Is it suitable if we give it to students for their thesis, their undergraduate thesis? Because for undergraduate thesis, I think they have very limited amount of time, like 4 to 6 months to study. Is it suitable for them? This question is for the three speakers.
So Professor Nakamoto should answer first. I'm already retired at university, so I have no responsibility for undergraduate students.
So yeah, I introduced very elementary graph theory topics. So I think some of our undergraduate students can study very elementary fact. Then I think some students can do something, I think. Yeah, that's all.
For me, it's a difficult question, actually. But as I told in my talk, if we consider some particular cases, only a fixed list or so small graphs, even for such graphs, there are some open problems, and I believe we should try those things first to solve for the general cases. So if I teach to my undergraduate students for that topic, I first ask them to read some proofs of our theorems, and then find some extension with maybe very restricted cases, but it's good to begin. And there are many important cases remains. Maybe that's only the small step, but that's necessary step, I believe.
Yes.
Yeah, it's all which I can say.
Okay, thank you so much. Yeah, I just want to give some idea for those who are new to this subject. So maybe we can start to explore this subject and start to do some small research on this subject. I think this kind of topics are really interesting for mathematicians especially. Okay, so is there any question from the participants? Enough? Okay. So I think that's all for the question and answer session. Let us thank again the three speakers for the informative and interesting talks. And thank you so much for the participants who are present on site and on the Zoom meeting. I hope that what we have learned today can give us broader knowledge and insight so that we can probably start research on this direction. Thank you, Professor Seiya Nagami, Professor Kenta Ozeki, and Professor Atsuhiro Nakamoto for the interesting presentation today. I hope that we can meet again in another occasion. Thank you.
Thank you. Thank you.
So we'll end this workshop here.
Okay. Nice MC.
Okay, see you. Bye-bye, everyone. Bye-bye to all the participants.